So in this unit, we've been talking about relations, linear relations, and specifically in the last few lessons, we've been talking about all the different ways we can use slope. So we can use it to measure how steep objects are. We can use it to describe rates of change of something. And in the last lesson, we talked about how we can use slope as a rate of change to convert units, which is basically what we're going to finish up with. Okay. Where am I? Now I lost my train of thought. Okay. So to convert units, in the last lesson, we converted rates of change. What if we want to just convert single units? Well, we can use conversion factors or slopes, really, as a rate of change to help us. So remember when I said you can always convert units by multiplying by a conversion factor. So just as an example, we'll take the first one. We want to convert 2 kilometers to meters. Now, for many of you, that may be obvious. You may be able to see it and say, oh, I times it by 1,000. And that's fine, okay? But sometimes it gets confusing because do you know whether to times or do you know whether to divide? Well, that's why conversion factors are so handy. So what I want to do is I'm going to make 2 kilometers a fraction by putting it over 1. Now, I'm going to multiply by the conversion factor between kilometers and meters. There's 2 ways you could write it, okay? You could write 1 kilometer up top and 1,000 meters on the bottom. Or you could write 1,000 meters up top over 1 kilometer on the bottom. They both mean the same thing. It's just the order. So I'm going to multiply this by one of these. The one that I want to choose cancels out the kilometers and leaves me with meters. So that means I need kilometers on the bottom to cancel out with kilometers on the top here. So I'm going to use this conversion factor. Because if I use the other one, I've got kilometers both up top. I can't cancel them out. This allows me to go, okay, kilometer, cancel each other out. My answer is going to be 2 times 1,000 meters divided by 1, which is just whatever the top is. So this gives me 2 times 1,000 meters, which is 2,000 meters. You can always convert that way by multiplying by the conversion factor. And the conversion factor will change depending on the question. A lot of times it's distance, metric distance. Sometimes it could be mass. Sometimes it could be between dollars and cents. Okay, there's all sorts. Sometimes it could be between US and Canadian dollars. Okay, the next one, 4 centimeters to meters. Well, first of all, 4 centimeters over 1. Now I got to multiply by the conversion factor that will cancel out centimeters and leave meters. Which one of these would I use? Centimeters, millimeters, meters, centimeters, or kilometers, meters? Meters, centimeters. But I want the centimeters on the bottom, right? Because I want to cancel it with the centimeters up top here. So Your conversion factor in this example is going to look like this. Notice we did it the other way around this time. We put the bigger number on the bottom because we have to cancel out the centimeters. So what does that leave us? Well, 4 times 1 is 4 over 1 times 100, 4 divided by 100. So notice in this case, we divide, and if you use your calculator and actually divide that, you will get 0.04 meters. Sometimes you may have to convert twice, like the next example. 3,600 kilometers to centimeters. If you look at the 3 above, there's no conversion from kilometers to centimeters. We have to go to meters first, and then from meters we go to centimeters. So we gotta convert this to meters first. And we're going to multiply by, well, there's 1,000 meters in a kilometer, right? Do I put the 1,000 up top and the 1 on the bottom, or the 1 up top and the 1,000 on the bottom? 1,000 on top because I want to cancel out the kilometers. Excellent. So that's going to give me 3,600 times 1,000, which is 3,600,000. You got 5 zeros? Yes. So that's meters. But now I got to convert that to centimeters. So I actually have to do 2 conversions. So I've got to take the meters I just got, 3,600,000 meters over 1, and use the conversion factor from meters to centimeters. So it's 100 centimeters is 1 meter, but I put the 1 meter on the bottom because I want to cancel it with the 1 meter up top here, which means I put the 100 centimeters up top. So I'm going to be multiplying again. So that 3,600,000 times another 100 gives me what? 360 million? Yeah, 360 million. So that's my final answer. You could have actually done both multiplications in one step and canceled out kilometers and meters at the same time. Or you could have done it in 2 steps like I did here. So the last one, 18.5 millimeters to meters. There is no conversion factor between millimeters and meters. I have to go to centimeters first. Then I can go from centimeters to meters. So how many millimeters in a centimeter? 10. But I put the 10 millimeters on the bottom because I want to cancel the millimeter units with those up here. So notice in this case, it's going to be 18.5 divide 10. which is going to give me 1.85 centimeters. I'm still not done because I have to go from now, take this to meters. So 1.85 centimeters over 1 times, now I got to multiply by the conversion factor between meters and centimeters. Well, there's 100 centimeters to a meter. I want the centimeters on the bottom so I can cancel with the centimeters up top here. So I would write it as times 1 meter over 100 centimeters. So again, I'm going to have to divide. It's going to be 1.85 divided by 100, which gives me 0.0185, sorry, meters. Conversion factors work nice because you're always multiplying. Like, yes, we ended up dividing after, but we always started with multiplying. Okay. Whereas if you try and maybe do it in your head right from the beginning, it might be hard to remember which one to multiply and which number to, or when you multiply and when you divide. Okay, so where can we use things like this? Well, scale factors. So this is the last thing we're going to talk about. Where do we use scale factors? When we talk about enlarged shapes or reduced shapes. Okay. Where do we use, scale factors are used on maps. Okay. You've got a smaller drawing of, say, the province of Manitoba on a map. And then there's a scale factor that tells you, okay, 1 centimeter on the map of Manitoba means 100 kilometers in actual distance. Okay. So that way we can draw a reduced version of the actual of Manitoba so that we can read it. How do we show them? Well, it's always made up of 2 numbers, and one of the numbers is always 1. So let's say the scale factor 1 to 50. That means that for every 1 unit on a scale drawing, okay, because the scale, we read the scale drawing number first. For every 1 unit on the scale drawing, it means 50 units in actual distance or whatever it is, or weight. Okay. So we can show it with units and words. 1 centimeter represents 50 centimeters. We can show it so it looks like a fraction, 1 over 50. Or we can show it with a semicolon instead of the fraction bar. So there's 3 different ways we could represent it. So say for this first one, I could also write it as the fraction 1 to 25, 1 over 25. Or, I don't know what the units are in this question, so I would say 1 unit represents 20 units. So that's 2 different ways we could show it. Here, well, we're given it in words, so we could show it so it looks like a fraction, or we could show it using a colon. But the only problem is the units aren't the same. So we can't go 1 over 6 and 1 to 6 because we want the units to be the same. So we either have to change the centimeters to meters, or sorry, to kilometers, or the kilometers to centimeters. It makes sense to change this. We need to change to centimeters. And how did we do that? Well, we did it on the last page. 6 kilometers over 1 times, well, I can't go directly to centimeters, but I can go to meters. 1,000 meters over 1 kilometer, and I write it like that because I want to cancel the kilometers. So that gives me 6,000 meters, but I'm still not in centimeters yet. So I have to take the 6,000 centimeters, sorry, meters, and convert it to centimeters. Well, 100 centimeters equals 1 meter. I want to put the 1 meter on the bottom, which means I put the 100 centimeters up top because I want to cancel the m's. And this time I am left with 600,000 centimeters. So therefore our ratios, it's not 1 over 6, it's 1 over 600,000, or 1:600,000. Okay, so where do we use these things? Like I said, maps was just one example. I mean, it's used in architecture all the time, right? Like if you want to draw, if you're planning a house for someone, if you're designing a house for someone, okay, you have to be able to put it on a, show it so that the person can see it right on a piece of paper. You know, might be a big piece of paper, which means you're going to take the actual house and you're going to scale it down to a drawing. But then you've got to also show that everything in the drawing has to represent the actual distance or weight or whatever of something. So that means scale factors deal with similar figures. In this case, we are given a reduced scale drawing of a dining room table so that it fits on a piece of paper. The actual dining room table is proportionally larger. We don't just make these numbers up from anywhere, okay? Like this means, if you look at this, the width of the dining room table is half the length. That means the actual table, the width has to be half the length. That means they're proportional. So we can be given the dimensions of the scale drawing, whatever the scale is. So that means that the scale, it would actually be 50 times, every dimension would be 50 times as big in real life. And then we're asked to find the dimensions of the dining room table, the actual dimensions. Here's how we can do it. We can always use equations, what are called proportional equations. These are handy to use. So how do we set up a proportional equation? Well, we know, use the scale drawing first. 1 to 50, that's the scale of the original, the scale to the actual. That's going to equal, well, I know the length of the scale, it's 5. I don't know the length of the actual table. That's why I write it as 5 over L. These will equal each other because they're proportional. How do we solve equations like this when you've got a single fraction on either side? It's very easy. Cross multiply. Cross multiply to get rid of the fractions. So if I cross multiply these, I get 1 times L, which is L, is equal to 50 times 5, which is equal to 250 centimeters. So that's the actual length of the table. Whenever you use a scale drawing to find out actual length or scale length, or whatever dimension you're asked, always set up a proportional equation. So for width, well, the original, every 1 unit on the scale drawing represents 50 units in real life. That will equal the width I'm given on the scale diagram over the width I'm trying to find in real life. Notice this is different from the previous stuff we did where we multiplied. Here we're making them equal. Cross multiply to solve. 1 times W is W. That will equal 2.5 times 50, which gives us 125 centimeters. So the actual width of the table is 125 centimeters. So that's going from a scale diagram to figure out actual or real dimensions. We could go the other way. You could be given the dimensions of the actual dimensions of something and be asked, what would it look like on a scale diagram if you drew one? Like the next example and the last example we'll look at. The length of an auditorium is 22 meters and the width is 14 meters. So we're given the actual this time. We are also told that the scale factor, 1 centimeter on a scale drawing represents 4 meters in real life. Well, we don't have to worry about changing this to centimeters because we can set up a proportional equation. So again, to find the missing dimensions, to find the length I would draw on the scale diagram, well, remember 1 centimeter represents 4 meters. I need to figure out what's the length on the scale diagram if the actual length is 22. So notice that it's flipped now compared to the previous example we did. But again, to solve, you cross multiply. So 4 times L, or 4L, will equal 1 times 22, which is 22. Divide both sides by 4, and you get, 5.5 centimeters. So on the scale diagram, when you drew the auditorium, the length would have to be 5.5 centimeters. Finally, to find the width, again, we use the original scale, 1 centimeter to 4 meters. I want to know the width on the scale, so I put the unknown up top, over the actual width, which I know is 14. Cross multiply. Four times W, or 4W, is equal to 1 times 14, or 14. And in this case, W will equal 3.5. Okay. So that takes care of that.